Kinetics review for AP Chemistry. First question that we have is pretty involved, but it looks at a lot of different angles with some information that's given to us. So at 40 degrees, hydrogen peroxide will decompose according to the following reaction. The following data were collected for the concentration of H2O2 at various times. So there's a time, and then there's some concentrations. So right away, what you could do is you could think about using your calculator and potentially graphing this out. But it's always smart to start looking at the questions that are given to you. So it says, A, calculate the average rate of decomposition between 0 and 2.16 times 10 to the 4th seconds. Use this rate to calculate the rate of production of oxygen. Okay, so what it's basically asking is, what is the rate of decomposition in this time frame? So when we talk about rates, rates are something you can measure over a certain amount of time, the change in a measurement over a change in time. So a rate would be the concentration. I'm just going to go with the data that's given to me here and link it together and make it fall under this idea. So knowing that, I have 0.5 minus 1.0 molar over 2.16 times 10 to the 4th minus 0 seconds. The calculation to that is negative 2.13 times 10 to the negative 5th. 3.1, I'm sorry. And that is for the hydrogen peroxide. Well, in general, what we can do is kind of ignore the negative and just say that is the rate of decomposition. So if I ignore that negative, that is just talking about a value. Well, this is actually asking about what is the oxygen. And the oxygen has a different mole ratio from the H2O2. So if I take this value, the best way that you can do to visualize this is literally do a mole ratio. So I have 1 mole of O2. I have 1 mole of hydrogen peroxide. And if you feel like those units aren't canceling out, inside the molarity, there is moles over liters. So if I would get rid of that for a moment and plug this in, it'd be moles over liters times seconds. And this moles right now is H2O2. So you'd be able to cancel that out and end up with H2O2. And I apologize, there's a small mistake. There are 2 moles for every 1 mole of those. So that's what we get for our oxygen. Letter B, what are these rates for the time period from 2.16 to 4.32? Well, let's plug that same idea in. And for these, ignoring the negative, for the hydrogen peroxide, the rate is approximately this. And if I divide that by 2, I get that for the oxygen. And you can see for both that the rates are decreasing, which is something that we have discussed. As reactions happen, less and less possibilities and collisions can occur, so reaction rates decrease over time. C, determine the order of the reaction. So how would you do this? There really isn't enough information. This is not a differentiated rate law problem where you can plug in different values and see how it affects the rate. The rate was not given to us yet. So when time is given to us, ultimately, you will have to potentially be prepared to plug this in your calculator with stat plot. A problem later in the review, I will show how you do this specifically, but you're going to use stat and calculations and lists. And by doing that, I determined, well, I'll give you a moment to check it out. So pause the video if you are interested in plugging this in. It's only 3 data points. It doesn't take a long time. What is the order of this reaction? You can also determine the rate constant pretty quickly from this as well. So give it a shot if you wish. By plugging it in, I found out this was first order. It gave a plot That was a linear relationship on the first order graph. Determining the rate constant, you just have to calculate that as well, and that can be done using your calculator with line rig, and you do L1, L3 in this case, and I got 3.21 times 10 to the negative fifth. 3.21 times 10 to the negative fifth. Because it's first order, it's inverse time, so that's 1 over seconds. So now it says determine the half-life. Well, because I know it's first order, I can make life very easy for myself. Half-life for first order is on my reaction sheet. And it ultimately comes from natural log of 2 over k. So if I plug in my k right here, I can get my answer. By maintaining some sig figs, I get 21,600 seconds. And if you're thinking, wow, that's huge. Well, if you look right back up on top, when you started with 1 molar of H2O2 and you ended up with 0.5, that's half of the amount. Well, look at that. There's my value right there. So half-life was already in my data. Lastly, it says calculate the concentration remaining after 8 hours if the initial concentration is 5.0 molar. That's where you have to plug it into an integrated rate law. So I'll give you a little bit of a hint. You're going to plug it in to this equation right here. Think about time units, please, and calculate how much will be remaining, which will be this value right there after 8 hours. So pause it and give it a shot. This is my starting point. I plugged in my K. This is my time. That's 8 hours times 60, which is then in minutes, times 60, which is then in seconds. Then there's my my initial concentration, which is 5.0. If I calculate that to a certain point, just for you to see where I'm at here, is that I get this value initially. To get rid of both sides, I will eventually take natural log to the e, which is second in natural log on my calculator. That will solve me for my x, which ultimately I find that after 8 hours, I'll have a little less than 2 molar of my solution remaining. So there is a very involved problem, starting with some simple rate issues, going all the way into an integrated rate law problem. Next problem. Derive the rate law expression and calculate the rate constant for the reaction A plus B plus 3C gives you a certain product, given the following data for 15 degrees. So you'll notice that someone has done 4 reactions, and in each reaction, the concentration of A, B, and C is given, and then the initial rate of the reaction is also provided. So you could have many questions off of this. And the first one would be, what is the order of this reaction? So to find the order, we need to isolate our compounds so we see how they affect the rate without the other reactants changing. Again, if I want the rate law expression, right now what you need to be thinking about is this. It's going to be rate equals K times A, B, and C, and then we're going to have a certain order for each. So you need to find those orders. So what I'd like you to do is take a moment, pause the video, and try to isolate each reactant so you can determine what the order is based on the change of the rate. So if you're having some problems with this, I can see why. Because B never seems to stay the same. So how would you incorporate that? Here is the hint. If that's going on, something else must be up. So if you look at these two reactions, where A is isolated and C is isolated, B doubles. And because B doubles and the rate does not change, B has to be zero order. Now what's significant about that is because if it's zero order, it has zero effect on the rate. So it doesn't matter that it's changing. So that's a little more advanced, to tell you the truth. But you needed to recognize that B is not affecting it. So I have the workout here for the A and the C. And what you can determine from this number is that when you take experiment 4 and 3, the concentration triples, and ultimately because of that, the rate went to 9.2, which is roughly second order. For letter C, with experiments 3 and 2, the concentration doubled, and so did the rate. So that would be a first order. So what does that entail then? That means that this is a 2, this is a 0, and this is a 1. So if I rewrote my rate law, it would look like this. My rate law would include the second order A and the C. How do we determine the rate constant? You've already done the hard work. You take your rate law now that is determined, and you simply pick a single reaction. So please pause it, plug it in, and see if you can determine the rate constant with the proper units. I determined it to be 0.375. If you're doing sig figs, 0.38. And then what are my units? I have a overall order of 3. So that means I need to get rid of 2 of my molarities. So there are many ways you could do this, but I'm going to do inverse molarity. I'm going to do 1 less than the overall order, and then I have to make sure I see the time, which is seconds. So it's 0.375 liter squared over mole squared seconds. Okay, here's a problem that is very typical in an AP question for kinetics, where it says the rate law for the following second order reaction at 10 degrees can be written as, and there's my equation. They give me the rate, here's my rate, equals K NOBR squared, and they give me the K. So they've given me actually a lot of information, but there's a lot of things that I can still show. It says determine the half-life when the original amount of NOBR is 0.650. Okay, I look at my equation sheet and shoot, I don't have a half-life equation. Now maybe you've memorized the half-life equation, but if you haven't, or if you have and you're unsure, using the integrated rate law equation is still the most important thing. So for letter A, what I'm going to do is I'm going to be plugging it in to the integrated rate law. It's always the y equals mx plus b equation, and in this case, I'm using second order. So second order is inverse concentration. So pause the video and determine its half-life. After plugging it all in, I took half of the original amount, used the K value, made sure it was all properly put and placed into a second order rate law, integrated rate law, and I got a half-life of 1.92 seconds. Letter B, calculate the concentration of NOBR at time 5.80 times 10 to the negative third seconds if, again, we start at 0.650 molar. Pause it and give it a shot, and in fact, see if you can go through all of this. I will do it piece by piece, but if you're able to do it without me, that's just better for you in the long run. My final answer would be 0.648 molar. Please be very careful to understand that when you are finishing this calculation that you have a 1 over NOBR. You have an inverted answer, so you need to take 1 and divide it by the answer you have to get to 0.648. So I'd suggest pausing it again, unless if you've already calculated it, and solve if the concentration initially is 1 molar, how long will it take for 50% of NOBR to react? By plugging it in, I got 1.25 seconds. Please be aware that this is a second order reaction, so it affects things a little differently. If you feel that it should work, well, it should have been half the amount. That is different for first order versus a second order value, depending on the relationship. So make sure that you're plugging it into your integrated rate laws. As you can see, I did it in the green. I got 1.25 seconds for that one. Lastly, letter D, calculate the initial concentration if it took 4.31 seconds for 75% to react. Again, pause the video and think about what that means. What is 75% to react? What does that mean for you with your integrated rate law? So here's the first thing you have to make sure that you're thinking about, is that when it says 75% to react, that means 25% of it remains. So looking at this, this could be a little more complicated and confusing because I have an original amount on the right and an original amount on the left, and I need to get that all together. I need to combine like terms. Rearranging and causing the concentration, initial concentration to be X, you end up with this relationship, and then you can solve for X, and X ultimately becomes 0.87 molar. The activation energy for a hypothetical reaction 2A plus B gives you C is 8.9 times 10 to the 4 joules per mole. If the original rate of the reaction is tripled at a temperature of 325 Kelvin, at what temperature did the reaction begin? So you have a reaction that's occurring and then a new reaction. So you're going to have two Ks, you're going to have two temperatures, and you're given an activation energy. So that is our given activation energy equation that we are going to be using, which is right here. And if you see an equation that has natural log of K1 over K2, you would simply see the T1s and the T2s flip-flop. So what we need to do is be placing the values that were given here. So one of the tricks is that it said that the original rate is tripled. So if the original rate, we're going to say, is 1, which would make sense, then what we can say is if that's 1, now it's been tripled. We can make any number we'd like. All right, it says the activation energy is 8.9 times 10 to the 4th joules per mole. Our R value is always the R value that deals with joules, which is 8.314 joules per mole Kelvin. And now we need to plug this in appropriately. So if we're looking at this and we want to make sure that we are pairing this up correctly, we know that the second temperature when it was tripled was 325. So we don't know the first temperature. Okay, that's kind of the goal of this. Now, you can figure this out in many ways depending on your mathematical abilities, but one suggestion I may give on this is just take a look at this first and view this as just X. So solve for this just as X, and then we can move on from there. If you're uncomfortable with that, we can look at it in a couple other ways. So pause the video and give it a shot. So this is my initial relationship. I took natural log of 3 over 1. I divided by 8.9 times 10 to the 4th, multiplied by 8.314, and I got that to equal X. Ultimately, that is going to be this. So you add 1 divided by 325 to the other side. That will equal 1x, and because x is on the bottom, you take the inverse, and ultimately you would find the temperature of 315 Kelvin. Here are two separate problems, both dealing with still the idea of activation energy, but also a couple other little things that deal with speeds of reactions, specifically catalysts. So first, the upper left one, the red problem. It says indicate how to measure the activation energy and the change in enthalpy. So if I have my reactants, and these are my products, and this is energy, okay, I need to just have an understanding of the differences between activation energy and change in enthalpy. Activation energy is the energy required to cause a reaction to occur. If they overcome that threshold of energy, the reaction will continue all the way to its products. So there is a peak. The highest peak of energy signifies that activation energy, and specifically, it's from the beginning of my reactants to the highest peak. If I want to discuss my enthalpy, it's the change in energy from the beginning to the end. So that is my enthalpy change. So that's how that one would look. And by the way, if we did have an endothermic reaction that would look more like this, let's say. This is activation energy right here, because this is my reactants and this is my products. But my beginning point is here, my ending point is there, so this is my change in enthalpy. So that would be the difference for that. Secondly, on the red problem, it says if the energy curve is an uncatalyzed reaction, draw an energy curve of a catalyzed reaction on the left. So what you need to realize is that a catalyst speeds up a reaction. By doing that, it lowers the activation energy. So hopefully you can see what I'm doing. I'm going to do it in black. It would be lower. So the peak would be lower. I still start and end at the same point. Okay. Second problem. It says a second order reaction has been plotted on the left. Draw the catalyzed reaction on the graph. I would like you to pause the video and process this. If that is the uncatalyzed reaction, what would the catalyzed reaction look like on that graph? Think about what a catalyst does. It speeds up the reaction. So think about it. Give it a shot. If a catalyzed reaction speeds up the graph, or a reaction, then a catalyst causes the rate to increase. And a rate on a graph is its slope. So I need to make the slope greater for a catalyzed reaction. So to make it greater, I need to make it steeper. So this is the catalyzed reaction, and this is the uncatalyzed reaction. Very important that you think about that in terms of the slope, which is the rate. Here's our next problem. Given the following information, calculate the average rate between 10 and 30 minutes for the production of NH3. They give you some data, they give you an equation, and you notice that you have columns of time and you have a column of concentration. And then we're given a bunch of things. Determine the rate law. I would actually like the rate constant as well, with units. Determine the integrated rate law, the half-life, and an amount required for 33% of the reaction to be completed, and then there's a graph. Once you see something like this, you should probably be thinking that you need to graph this in a calculator. So I'm going to give you the opportunity to pause this and plug it in on your own in your stat plot and lists and stat calculations and graphing to find the linear relationship of this data. I'm going to transition over to showing you how I'm going to do it in my actual calculator, and then we'll come back onto the main screen as well. So please take this opportunity to determine the rate law, the rate constant, the integrated rate law, and if you can, graph that. The rest of it will come back onto here. Okay, so we have this information now from using our calculators. We can continue on from there. It says determine the half-life. Well, but because I know that it is a first order reaction, I can utilize my reaction sheet again. I can utilize this equation. Now, if I didn't want to do that, what I could do, just so you understand, is I could plug in this amount for here, and then I could take 50% of my original amount. But I'm not going to do that. Plugging that in, I get a half-life of 21.4. Make sure you look at the units, minutes. Finally, determine the amount of time that is required for 33% of the reaction to be completed. Take a moment and finish this calculation. Plugging it in, I made sure I understood that 64% of it is remaining. So I took 0.64% of my original, plugged in my K. My original is still 0.134 or 0.13, and I got a time of 13.8. And then I got to check my time again. Minutes. That's how long it would take for 64% of it to remain, or 33% of it to react. All right, let's change gears a little bit. It says write the rate laws for the following proposed mechanisms for the decomposition of IBR to I2 and BR2. So there's two different reactions here, A and B. A, you have 3 reactions. B, you have 1. So when you take a look at a problem like this where there's 3, there is an overall reaction that occurs. Things cancel out on the products and the reactant side. So on the right side here, what I'd like is the rate law, the catalyst, and the intermediate. But first, I'd actually like to focus on the catalyst and the intermediate. So pause the video, look through the problems. What I'd like you to do is add up these equations, cross out what you need, what is the final equation that you have, and then what is a catalyst and what is an intermediate. From there, we can figure and determine the rate law of this reaction. So I added up the equations, but I want you to visually see how I'm crossing these out. So I see I right there, and it cancels. They're on the opposite sides of the equations. I see a BR and a BR. I see another BR and another BR, and I believe that's it. So the key to this now is how they were introduced. When did they show up in the reaction? So it matters the order. So I is crossed out right here, and it was created, then consumed. So that must be an intermediate. Okay? The second one, BR, was produced, then consumed. So BR is an intermediate. Lastly, I take a look at that other BR, and that other BR was produced, then also consumed. So that is an intermediate. So there are no catalysts in this reaction. The only way for the catalyst to be in this reaction is if, this is just hypothetical, if these two were flipped, let's say, and then I was produced, or was introduced as a reactant, then produced in the second reaction, but it wasn't. Okay, so what is my rate law? Well, according to what we discussed with molecularity, if you're given different reactions, you have to have the rate law reflect the rate determining step. Which one is the rate determining step? The slowest step. So all I need to do is look at the reactants that are involved in there. So I look at it as rate equals K times IBR, and because there's only one of them, it is first order. I understand that the equation has a 2 there, but I was given more information, and that information showed me the rate determining step, which is the slowest step. The second one, all it is occurring in one step. And I know that it looks exactly the same when I write this back out again. It looks like this. The difference is that we're saying this happens in one step. So because there are 2 of these, the rate law for this one, based on molecularity and molecular collisions, this is a second order reaction rate. So that is the big difference. You always take it off of the rate determining step. If you have no other information, then you have to go off of what you were given, which in letter B, that's all we had.